final exam review session for 1022. I'm John, this is Stephen. We know you guys know us probably by now. So the way we're going to do this is probably similar to the way we've done it in the past, and we're probably going to devote about one question to each topic, because there's quite a bit for you to cover from all three exams for us to cover in 2 or 2 hours. So we'll do 30 minutes roughly for the first exam, 30 minutes for the second exam, 30 minutes for the third exam, and then the last 30 minutes can be general questions that you all might have. Okay? So, we can go ahead and get started. Can y'all see that? Or did it change the lights at all? Okay. Alright. Is it too dark? Is it too dark in here? Okay. Yes, that's. Let me turn the brightness. Is that alright? Is it too bright? I guess we're going to assume it's alright. Okay, so we've got a boiling point of an aqueous solution of magnesium sulfate. It's 103 degrees, and it's asking what mass of the salt is dissolved in the 1 liter of water to make this solution. So, you'll remember that the delta T, B, is going to be equal to, remember this? It's going to be the Van Hoff factor I times the constant for the boiling point elevation times the solution's molality. So, we know then that delta TB is what? Is going to be 103 minus 100, which is 3 degrees. And Van Hoff, or the boiling point elevation constant for water, that will be given to you on your exam, so you won't need to remember that. And if you look on the front page of your exam, you'll find that it's 0.512 degrees Celsius per molality. Now, what about I? For magnesium sulfate, what is I? 2? Why do you say 2?
2 moles of ions per mole.
2 moles of ions per mole of salt. You see, 1 mole of, you can do magnesium, which creates one of the ions, and sulfate, which creates the other ion. So in this case, I is 2. Okay, so then we can say, well, we can solve for molality. So we know that molality is going to be equal to delta TB over I times KB. And that would be equal to 3 divided by 0.512 times 2. Am I going over too far? No, that's okay. 3 divided by 1.512. I do this, I get 2.93. Remember, this is molality, so our units here are moles per kilogram. And that's moles of solute per kilograms of solvent. And if we have 1 liter of water, that is what 1 liter of water weighs 1 kilogram. So in 1 liter, we have 2.93 moles. Okay, so 2.93 moles. 2.93 moles. We need to convert this into grams, and the molar mass is given to us as 120 grams per mole. So we take 2.93 times 120. Moles cancel, and we're finally left with 352. Any questions on this one? Yeah.
Why is it 3 degrees rather than 102?
Because it's the delta change.
Okay.
So it's the change in temperature. So we're looking at water normally boils at 100 degrees, and so we're taking the change from 103 minus 100 gives us 3. Besides, if you put 103 into this equation, your numbers would be way off. Okay, moving on. Ready? Okay, so this question is about intermolecular forces. So we're going to cover interactions between two different molecules. The question is, what would be the strongest type of intermolecular attraction between the two different components in each pair of molecules? In pair number 1, we have iodine, molecular iodine, and cyclohexane. And in pair number 2, we have ammonium nitrate and water. So basically, this requires you to go through the list of answers kind of and eliminate them based on the shapes and charges of the molecules. I can't fit all of mine here. All right. So first off, what do we know about iodine and cyclohexane as far as charge goes? Do they have any charges, any ionic interactions? Oh, good. Okay. So iodine and cyclohexane are both pretty. Not only are they don't dissolve into, they don't produce ions when they dissolve in something. They're both pretty symmetric molecules. So I'm going to cover this up for just a second. So when you have iodine, you basically have something that is perfectly symmetrical, and cyclohexane is also symmetrical or isotropic. Those two aren't going to have any discernible dipole moment. So those ion-induced dipole interactions on pair number 1 on the left up here can all be eliminated. So we can easily take off A, B, and C. And so the next thing we're looking at is pair number 1, hydrogen bonding. Now, are those hydrogens on cyclohexane going to be available for hydrogen bonding? No. All right. They're all attached to carbon. They're all pretty much nonpolar, so they're not going to interact. So we can't and iodine doesn't really have any
receptor sites for hydrogen bonding. So those are all gone, and we're just looking at the last ones. And this should make sense over here, these last three being dispersion forces. These last three options being dispersion forces for pair number one, because they're nonpolar molecules, the strongest is dispersion. And then pair number two, we've got ammonium nitrate and water. So ammonium nitrate is an ionic salt, right? So it's going to turn into ions. So we're going to have some form of ion interaction with the other compound. And there aren't, well, I'll leave hydrogen bonding on there because it could be a possibility. And then we've got water, which is a somewhat asymmetric molecule. If we look at it over here, we've got water like this. And what you should know is that water has a permanent dipole moment, right? So it's got these electron pairs over here and the hydrogens over here, which causes a dipole moment, which I want to draw it the right way. Towards the positive,
Toward the negative.
Towards the negative, right.
The arrow goes towards the negative.
So the dipole moment's like this.
Because there's a plus sign on top and a plus pointing towards the
I have never known that.
Yeah.
Okay, so if you're drawing dipoles, the plus goes towards the plus. So water has a permanent dipole moment, and ammonium nitrate is an ion, so that would seem to suggest ion dipole, right? So we've got an ion interaction with a dipole. So that gets rid of this, and the answer is G. Do we have any questions about determining intermolecular forces between molecules? This is way back at the beginning of the semester, so. Does that make sense? It's basically a matter of either picking which ones make the most sense or eliminating the ones that don't. Pretty close.
No, not close.
Okay. You might just have to write it up there.
All right, we'll just do this one without choice.
Okay. Okay. This is kinetics. By monitoring the disappearance of a reactant in a first order reaction, the half-life was determined to be 15.2 times 10 to the minus 6 seconds. How long does it take to decrease the initial concentration to 1/4 of its starting value? So you have to remember what a half-life means. The half-life is the amount of time it takes for the reactants to be decreased by 1/2. And so what we would see is that because we want to go to 1/4, you can see then that 1/2 times 1/2 is 1/4. So we're looking at 2 half-lives. If that makes sense. Trying to get it to 1/4, and so in order to get it to 1/4, you would reduce it by half the first time. You'd have half left. You take that half, cut it in half again, and you're left with 1/4. So 2 half-lives, and so that means that you take this time times 2. So you take 15.2 times 10 to the minus 6 times 2. And that will give you 30.4. I am. Almost.
Oh, man.
Now, I didn't write the answers up there, but that's not one of your choices. You would recognize then that 3.04 times 10 to the what, if you were going to change that around a little bit. It would be times 10 to the 5th or 10 to the 7th.